8.6, scale factors in 3D objects. Complete the following table. So we did one very similar to this with our area and 2D objects. So it'll work the same way, except we're going to be talking about our surface area and volume now with 3D objects. So sphere A. I have a radius of 1. What would be my surface area? So surface area of a sphere, let's just write that out first. 4 pi r squared. And the volume of a sphere, the volume is 4 over 3 pi r cubed. So when my radius is 1 squared in here is 1 times 4 pi. It's just 4 times pi, which ends up giving us 12.57 centimeters squared. The volume for that then is 4 over 3 times pi, 1 cubed, so just 4 over 3 pi, which is 4.1. Just leave a few decimals there. Second sphere, for sphere B, my radius is 3. So 4 times pi times 3 squared, which is 9, gives us 113.10. And 4 over 3 pi times 3 cubed, which is 27, gives us 0.997. Just adding units, centimeters squared. These ones should have centimeters cubed. And the third sphere, sphere C, has a radius of 5. So 4 pi times 5 squared is 25. 314.16 centimeters squared. And then 4 over 3 pi times 5 cubed is 125, which will give us 523.5988 centimeters cubed. Okay, so that is our spheres with our radiuses given. We found our surface area and our volume. Now we're going to be comparing sphere A to B and finding the scale factor that would have been used and the ratio of their surface areas together, similarly like we did with in our area section. So sphere A to B. So I'm starting with A and I got B as my image. So image over your object. So B over A is 3 over 1, which is 3. My scale factor is 3, an enlargement of 3. A to C, so C is my new one. C is my image over my original, which is A, 5 over 1. Oops. And B to C, so I got C after starting with B is 5 over 3. Which is 1.6. So the ratios of surface areas now with those two. So surface area of B was 113.1. Yes. Over my surface area, the first one, which is 12. Just making sure those numbers are right. Over the surface area of A. Gives me 9. Ratio of A to C. So C over A is 314 over A. Divided gives me 25. And B to C, so C over B gives me 2.7, repeating. So ratio of the surface area, now ratio of the volume. B's volume over A's volume gives me 27. C's volume over A's volume gives me 125. And the last one, C's over B's, so 523 over 113 gives me 4.63. So now we want to look at those to see if we recognize a pattern. So what relationship is there between the scale factor and the ratio of the surface areas? We can see that the surface or the scale factor squared. Whatever our scale factor is, we square it is the ratio of the surface areas. So our object of our area times our surface area squared would give us our image area. So the ratios of surface area is our scale factor squared. What is the relationship between the scale factor and the ratio of the volumes? Well, if my scale factor is 3 and my volume is 27, scale factor is 5, my volume is 125, I can start to see that I'm cubing those. 3 cubed is 27, 5 cubed is 125, 1.66 cubed is 4.63. So the relationship here is the ratio of volumes is your scale factor cubed. So when we're doing work, when we get into our equations, our scale factor cubed will give us our image volume over our object volume. And we could write the same thing for our surface area too. So our scale factor squared would give us our image area over our object area. So now let's try some of that in some examples. So example 1 says, prove the scaling conjectures for the surface area and volume of a rectangular right prism with dimensions length times width times height. So show that what we just said in that chart is going to hold true for this as well. So if I have volume, let's just draw a rectangular prism. Like this. And length, width, height. So the volume for this shape would be length times width times height. Now if I want to scale that by some scale factor, which is just x right now, I will get another object similar to this. That is my length times my scale factor, my width times my scale factor, my height times my scale factor. So the volume in this one is length x times width x times height x. So if I factored out an x from all of that, I'd have 3 x's. X cubed times length times width times height. So I can see now that whatever my scale factor was x, if I cube it, then I'll get my volume of my enlarged one. And it wants us to do the same thing for surface area. So for this first one, surface area would have been 2 times length times width plus 2 times length times height plus 2 times width times height. Now for surface area of this one, it would be 2 times length times width times your scale factor plus 2 times your length times your height times your scale factor plus 2 times your length, times your width times your height times your scale factor. And these would all have your x's, so squared. Sorry, I'm going to rewrite that so that's clearer to see. Length times your scale factor, width times your scale factor, plus 2 times your length times your scale factor, height times your scale factor, plus 2 times your width times your scale factor times your height times your scale factor. So to simplify that, I could just have length times width times scale factor squared, plus 2 times length times height times scale factor squared, width times height times scale factor squared, since there's 2 x's inside of each of those brackets. Factoring out my x squared, I would have 2 length times width plus 2 length times height plus 2 width times height. So that's my original surface area multiplied by my scale factor squared. That's exactly what we talked about in the tables before. So our volume should be our original volume times our scale factor cubed, our original surface area times our scale factor squared. That's just a proof. That wasn't solved. We didn't end up solving for a value anywhere. That's just showing that, in fact, all the table work we did at the front of your notes for this section works for a rectangular prism. We just put it into an example form. Now to do some solving. Example 2. A plane parallel to the base of a cone divides the cone into 2 pieces. Find the ratio of the surface area of the small cone to the surface area of the large cone, and the volume of the large cone to the volume of the small cone. So a plane parallel. What that means is just a line parallel to the base of the cone will divide the cone into 2 pieces. So if I were to draw a cone like this, what it's saying is that there's a plane parallel to that bottom that's going to cut these cones into 2 pieces. So I have a full-size large cone from here to here, but I also have a small cone here to here. So it says the dimensions are 3 centimeters, and this is 5 underneath of it. So we know that the whole height of the large one must be 8. So this is just a cone. I gave you those dimensions. They're not typed in there. I should have put them in there. The small cone is 3. The bottom half of that cone is 5. So if I drew them separately, just to see the cones on their own, this is 3 centimeters. And the large cone again is 8 centimeters. Large to small. So the surface area of the small cone to the surface area of the large cone. Surface area of your image over the surface area of your object equals your scale factor squared. So this was our formula from before. My image was 8 because I'm the surface area of the small to the large. So large goes on first, large is my new, over my small one, which is 3. And that needs to be squared. So 64 over 9. And then the volume of the large cone to the volume of the small cone. We're just showing again using the cubed and the squared. Volume of your image over volume of your object is your scale factor cubed. So now I'm going large to small. So now small will be first, whatever I'm going to, over what I started with, cubed. 3 cubed is 27, 8 cubed is 512. So those are just the ratios of those two things. It said to find the ratio of the surface area, find the scale factor, and for the volume as well. So the only thing you have to remember, normal scale factor is image over object. If we're finding that with the areas, then it's your scale factor squared. If we're looking for that with volume, it's your scale factor cubed. Example 3. Two cylinders are similar. The radius of the larger cylinder is 3 meters, while the radius of the smaller cylinder is 2 meters. The surface area of the larger cylinder is 54 pi meters squared. Find the surface area of the smaller cylinder. So I know that I have a smaller cylinder with a radius of 2. So the radius there is 2. I know I have a larger cylinder with a radius of 3. This one has a surface area of 54 pi. And this one has a surface area of unknown. That's what we're looking for. Find the surface area of the smaller cylinder. So again, surface area of your image over surface area of your object equals your scale factor with area squared. So if I'm looking for the surface area of my image, I'm going to multiply this side by the surface area of my object. Which is what I know. So I'm trying to scale down to the surface area of the smaller cylinder. Surface area of the image equals my scale factor squared. My scale factor is I'm going to the smaller one that has a 2, and I started with the larger one. So it's 2 over 3, image over object, squared, times the surface area of my object, which is 54 pi. Two squared is 4 over 3 squared, which is 9, so 4 over 9 times 54 pi. And just simplifying that, 4 times 54 over 9 is 24 pi. That is the surface area of my smaller cylinder.